Hello, can everyone hear me? The mic on and everything? Good to go. Thank you, Boodle, and thank you for having me here. All right, I had a totally different talk planned, and then Phil's talk was really cool. And then I was like, oh, well, I'll do something with Lambda Calculus and miniKanren. And then I was talking to people last night, and basically Andrea and Mark and Stefan and a few other people convinced me to try something like much more radical than I normally do with my live coding. So I want you all to be doing live coding, or at least anyone who's interested. So if you can get out your lappies and go to this URL, and that holds doubly true for anyone watching on video. This is specially designed so that people in the audience and people on video can kind of follow along. And basically what I'm going to do is I'm going to check in the code as I'm talking, and I'll let you know when I did a check-in. So you can do a poll, so you can sync up with me. And there's a really cool web-based version of miniKanren that David Kahn created. And you can just paste that code into the web browser, and you should be able to run miniKanren. Okay? So we'll try that, and it might crash and burn. We'll just see how it goes. But the great thing is if someone's watching the video afterwards, they should be able to follow along and stop. And if anyone here is confused about something, and you can't get an example to run or whatever, you can ask a question, okay? Or you can take it offline, whatever. But it's one thing to show this stuff, but at some point people have all these questions, and if you can't really play with it, you don't really get the sense, I think, of what it's about. So I want everyone to be able to try it. Okay, so the web browser version of miniKanren is at this link right here, the Venire stuff, okay? All right. So here's my repo, and I've got a file called talk.scm, and that's where I'm going to have my code in it. And the way I'm going to do this is I'm going to basically type into the code into Emacs, and then I'll paste it into Venire. And that's basically what you all can do in terms of opening up the file and pasting into Venire and running it. And you can edit it in your own text editor. You can edit it in Venire. And I encourage you to try some different combinations or different queries and see if you can break it, see if you can run in infinite loops, which you probably can, and so forth. And if you have a cool example, you can share it. This is, by the way, like version 0.01 of the technology I would really like for giving interactive talks, where either super Emacs mode or a web browser or something like that, where people in the audience really could do this more seamlessly. But that's tech I'm working on with other people like Michael Ballantyne. All right, so let's talk about miniKanren. And I'm going to bring up the Venire editor. Let me refresh. If Venire ever gets in a bad state, you can just click refresh. Let's see, I can kind of make the font bigger. The way you use Venire is if you've got code on the left-hand side, you click the run button, and it'll evaluate this code. And there's like a little read eval print loop thing you can just type for small expressions if you want to try those. Okay? And this is a relational scheme interpreter, which we'll play around with something like that in a minute. The main button you're going to care about is this create file button. So if you create file, it's going to blank whatever's on the left. And you can just type in code here, miniKanren code, and then click run, and it'll be evaluated on the right-hand side. So let's just try something simple. So I said I'll go to Emacs, but well, let me try doing it in Venire. First of all, is the font big enough? Can people see that? I can try to bump it up a little bit. If the run button will cooperate. Maybe I can, there we go, look. That run button's oversized. Okay, so the first thing I'm going to show you, so miniKanren, core miniKanren only has 3 operators. It's a very small language, just like Lambda Calculus is very small, right? Lambda Calculus has 3 parts, and so does miniKanren for the core parts of the language. And you can extend it, just like you can extend miniKanren to get something like scheme, right? So the most fundamental operator in miniKanren, and miniKanren's a type of logic programming language like Prolog. It's got some real differences, though. The fundamental operator is something called unification. And unification you can think of as sort of like a two-way super pattern matcher. So if you're familiar with pattern matching, then in a pattern match, you have some value you're pattern matching against, and then you've got some sort of pattern, right? And in the pattern, you can have variables. We call those match variables or pattern variables. Okay? And those pattern variables get values filled in from the value you're matching is. Similar with unification, except you can have essentially pattern variables on each side. Okay? So you can have variables on both sides. And the variables don't actually ever have to be filled in. And that's fine also. Variables don't ever have to get values in this paradigm. So here we're going to do something simple. And you can also think of unification, we call it equal here really, as like a type of equality operator also. So here we're asking whether or not 5 is equal to 5. Or another way to look at it is we're asserting that 5 must be equal to 5. And if it's not equal to 5, then we've reached inconsistent conclusion basically. So is 5 equal to 5? One would hope, okay, yeah. The logic isn't that weird, so let's run it. And you can see, copy the expression, and the answer is yes. Well, that's good. That makes me happy. All right. Okay, so I promised I would do the interactive thing. So here's our first program. Equal 5, 5, and I will check that in. Okay. So, are you supposed to like, how do you do this thing? You do like a get add or something? Get upload? Add dot. Oh, whoa, okay. And I'm not really good at get. So, and then get commit, is that how you do it? Oh, you have to do it. Okay, so get commit, and I have to give a message, and I'll say 1 is the message, because that's the first one. Okay? All right, so you're following along, that's the first. So you can do a pull, and you can paste that complicated program into Venire. Let's all do it, make sure we get the tech working, and then click run, and you should be able to see yes, okay? So that's the first program, great. Okay,
Will,
yes?
for future reference, instead of doing the git add, you can just put a -a on the git commit.
Git commit -a, ooh, yeah, okay. All right, I like this, I'm learning. Okay, so we can do another program. Let's do a variant. This is program number 2. What about 6 and 5? No, that's right. Computer says no. All right, so.
What about the proof of this?
The proof of it? Okay, what is it? Well, hold on, let me check in my code, I promised. Okay. I guess I could like, look, like Git keeps track of revisions. So I'm not even going to add another expression. I'm just going to like do that, and then it works, right? So I could do git, was it? Git commit -a, woo, -a, and then 2, right? Do a pull. Okay, so what's your question, Boodle? You want to know about the proof?
Yeah, why is 5 equals 5 to 5?
Why is 5 equal to 5? Well, let me change it up a little bit, and maybe I'll answer your question. I'm going to put in something else. Instead of a number, instead of having 2 numbers, I'm going to put in x. And x is a logic variable. So you can think of it sort of like this pattern variable, right? Okay, so is x equal to 5? Yes, we don't know yet. Okay, we don't know. It could be. If x doesn't have a value yet, then now it does have a value, right? The answer is yes, and x is 5. But if x is already 6, then the answer is no. All right, so we don't really know, but I'll say that x is starting out fresh. We say fresh, it doesn't have a value yet. So let's run that. Yes, and beyond yes, we see that x has a value associated with it, 5. Okay? All right, cool. Yeah, what? Why didn't that work?
Didn't save.
Oh, I didn't save? Oh, you're right. Okay, this is hard. Okay, all right. So that's one thing we can do. All right, and so if you look at it this way, then basically what we're really saying is an assertion. We're saying that the thing on the left is syntactically equal to the thing on the right, as long as you can find some set of values to assign to these variables inside the terms that will make them syntactically equal, right? So the question is there any possible assignment for x that will make the left and right-hand side equal? And the answer is yes. As long as x is 5, then they'll be equal, okay? So that's the sort of reasoning you do with unification. And we can even put variables on both sides, x and y. So what should the answer be here? Yes, and furthermore, what else do we know? We know that y is 5. Well, let's say we got rid of the original program, right? This is the whole program now. So there are no 5s anymore. X and y are the same, presumably. And so we can see here that x and y are both associated with some value. And this itself is a representation of a logic variable that doesn't have a value. And you can see that they have the same number. If they were different, you'd see a 1 here in one of them and a 0 in the other. So it's telling us it really is the same logic variable, okay? All right. I'm going to get the hang of this soon. So
the definition of equality there, that's axiomatic in it?
it's basically a syntactic definition, yeah. So you could define it recursively, like over a tree. Okay, so that's the big operator. And of course, we can have more complicated data structures. So we could do, I think Venire has this. Let's see if Venire has list. Yeah. So Venire has list in it. So we're creating a list containing x and a list containing y. And because they have the same structure, that's fine also, okay? But if we had, say, list x and y, well, what would happen in this case? Is it going to succeed? Is it going to fail? It's going to be yes. And notice we have the same logic variable here for the x, but now y wraps a list around it. Okay? Yes?
Why do you use logic variables as opposed to creating a substitution that says x equals y, y equals x?
So that's a good question. Internally, there is a substitution. The question is about why aren't we using a substitution? Internally, there is a substitution, and this is actually the representation of the substitution, okay? We're seeing as the output the representation of substitution. All right, here's one more. List x and x. What's the value there? Yes, no? What should it get printed out as? Infinite tree. No. We're not allowed to have a term unified with a term, with a structure containing that term, okay? And this gets to what Phil was talking about, where you can have these infinite structures and you run into trouble with that. So we're doing what's called the occur check. We're checking to see if x occurs in the structure, and if so, we're going to say no. No answer. We fail, okay? And that's important. This is how we get soundness. If we don't have that, we can prove all sorts of things that aren't true and get in trouble. Okay, so that's unification. That's the main operator. What else do we have? Well, we have the ability, yes? Question, Rob?
I couldn't get it to fail on more than one term.
You couldn't get to fail on more than one term. So
if there's unification between x and 5 and then again between
I see. Okay, good question. Good point. So I think what Rob's saying is if you do something like this and then you have another equal, and we're saying 6 and x, right? Then you think that's inconsistent information, but we're still getting a yes that x is 6. So let me go ahead and show you how we can sequence things. So what Venire is doing is it's assuming these are two separate programs. It's ignoring the first, essentially, and just giving us the answer from the second. That's a good point. So let me show you the second operator of miniKanren, which is called fresh. And what fresh allows you to do is a conjunction. Okay, so now we have a conjunction of goals, like that. And I can run that. And now my answer is no. Okay, so fresh acts as a conjunction. Fresh has one other purpose. Fresh also lets me introduce new logic variables. Now, the way Venire works, which is a little different from standard miniKanren, Venire acts more like Prolog, and these variables that aren't defined lexically, those become new logic variables. So you need to use fresh less in Venire than you do in standard miniKanren. But if we add a y there, that will allow us to create a locally defined logic variable that has no value called y. Okay? So that's the fresh form. All right, that's a pretty complicated program, so I better add that. And yeah, okay. All right, good. So you've seen 2/3 of the language now, fresh and equal. And then I'll show you the last part. The last part's condi, and this is something that allows us to get more than one answer back. Okay, because it'd be kind of boring if our programs could only return one answer, one of the points of logic programming is that we can return potentially infinitely many answers. So the way we're going to do that, and miniKanren syntactically looks a lot like Scheme, because the original implementation was Scheme. So cond is based on Lisp's cond operator, which is a conditional operator. It's sort of like a big, giant type of if or pattern. It's sort of like a pattern matching syntax, but it doesn't have a pattern matcher built into it explicitly. So we're going to have a cond here. Cond. E stands for every answer. And the syntax for a cond is that for each clause, each cond clause has a set of parentheses, and then it takes one or more of these sub-expressions, these other miniKanren expressions, which are called goals. Okay, so equal 5 x is a goal. I'll plop that in there. And equal 6x is a goal. I'll plop that in the second case. Okay. And all right. So what's going to happen here? Well, the idea is that we're trying each of these two clauses independently. We're going to try one of the two clauses, and it's unspecified in miniKanren which one we try first. Let's say we try the second one first. So we would try unifying x with 6. We'd get a yes, x would be associated with 6. And then we could ask for another answer. And we ask for another answer, it's as if we had never tried this one. We try the other one. And now if we get this association between x and 6, x is refreshed magically, and we're going to try it again, and now x will be 5. So it gives us a chance to try different branches of a program. So it's similar to like an if, except an if where you can independently try all the possibilities, all the tests and the consequence and so forth independently. Cond is like a disjunction, and fresh is like a conjunction. Cond is disjunction, fresh is conjunction. That's right. Okay. And there's a simplified version of miniKanren called microKanren, where conjunction and disjunction, binary versions of those, are the primitive operators. So those are much closer to logic. This is closer to maybe a nicer syntax to program with for real programs. But if you want to see the more primitive stuff that's closer to logic, look at microKanren. And that has the very short implementation. The implementation of microKanren is something like 46 lines of scheme code for all the logic programming system. So we can try running this, and we get the first answer. So we try the first one. First clause in this version of miniKanren, and we can click on more answers, and hey, now we've tried the other clause where x is 6. So we're not inconsistent because we're trying these clauses totally independently of each other. And we can ask for more answers, and finally we say no more answers. That's it. Okay? And if you've ever used Prolog, this part is very similar. All right, and that's the entire language, the entire core language. There are basically 3 other operators that we might run into, but that's the basis of it. Okay? Any questions? Who's playing along, by the way? I'm just curious. How many people? Oh, whoa, that's pretty good. All right. So now let's try something more complicated. All right. All right, let me keep myself honest. And check myself in. All right, and our programs are going to become more complicated here, so the check-in thing will be a little, whoops, oh. I checked that in as 5. Oh, here. I'll hack it. I'll put in a space and check it in as 6. Yes. I need to work on my Git skills. That's fine. Oh, I need to push. Yeah, thank you. Yeah. My dream tool would have me not have to do this step. All right. Okay, so let's try something a little more interesting. So Phil was talking about lambda calculus yesterday, and he showed that there are 3 basically parts of lambda calculus. So you have variables, you have lambda terms themselves, or which are called abstraction in lambda calculus, and then you have application, applying something to something else. So we have these 3 things, and if I write down comments, hopefully Venire will check on this. So we have something like x is a variable, and then we have something like I'm going to write it in sort of like the schemely way, like lambda x y. Right? So that's an abstraction. We call it ABS. And then you have something like an application. So we're applying F to G or something like that. Okay, so that's an application. So those are the 3 syntactic forms that we have in the lambda calculus. So let's try just writing something in miniKanren that will actually recognize a valid lambda calculus term syntactically. Okay, so let's just try doing that. So how should we do that? Well, we're going to define a function. So this part is pretty much like scheme. Let's try defining a function. And so let's call this, I don't know, lambda calculus syntax, syn, LC syn, okay? And because we're in a schemely language, we're going to ourselves define this function using lambda, and we're going to give it some argument. So I'll say we're taking, well, a term, a lambda calculus term, okay? And now what we want to do is basically match against the three possible terms. So which form do you think I should write here next? Or which miniKanren operator? So I got kandi, because I have choices to make, right? So I've got kandi, and how many clauses am I going to have for this kandi? Three, okay? That's right. So I'll go ahead and write down my clauses to begin with. All right. And now what I'm going to do is for each of my syntactic forms, I'm going to write down a clause for that, okay? So let's start with, I don't know, the application term. All right, let's do the lambda term, actually. Okay, so what am I going to write? What sort of miniKanren expression am I going to write in that clause to match against the lambda? I'm going to write kandi, I'm going to write a fresh, I'm going to write an equal equal. What would I use for pattern matching, basically? Equal equal, right? That's sort of like the two-way super pattern matcher. So let me write an equal equal expression, unification expression. And what am I going to unify? I need two terms, two values. So I'll unify what? Term, okay, the term that came in. That's right. And I'm going to unify that with, well, something that looks like my lambda expression, right? I have to write something down that syntactically looks like it. Okay, so what I'm going to do is I'm going to just copy this thing. All right, and I wonder if I can ninja it a little bit. Oh, look at that. Yeah, okay. All right. So that's kind of what my expression looks like. Now, there are a couple things here. So I've got like x as a variable, and this thing in the middle is really like the body expression, or e, or t, some other term. Okay, so we got a variable and we got some term here, and to make this schemely, we need to make this not a lambda expression in miniKanren or scheme in the host language. We need to make this a data structure that we can literally pattern match against. So we're going to create a list. And the one way to do this in scheme was with this backtick operator, called quasi-quote. And it's sort of like a string interpolation style thing, if you're familiar with that. Basically, if we put a comma in front of sub-expressions, that means that these things here are going to be literally filled in. They're like holes to be filled in with whether the values of x and t are at that time. And we need to have some x's and t's here. So what I'm going to do is I'm going to create a fresh so I can have two new variables for x and t. Okay, so I'm creating two new logic variables. And I'm going to grab that. And I might have to drag this even more. All right, there we go. Perfect. Okay, so when we're writing these sorts of programs, it's good to try to test them sort of incrementally. So what I'm going to do is I'm going to temporarily comment out the first and the third clause with the comments and scheme, and I'm going to just try running this thing to see if it works, because I'm not sure if it will, because I don't use Venire normally. So let's see if it works. Hash t. Ah, cool. Okay. Because we didn't actually call it. So we can actually make a call to LC syn now. So let's try calling LC syn, and let's give it a term. So let's give it, the term lambda z, and see if that succeeds. And it says yes, it does succeed. So this means that this is syntactically valid. Great. Okay. So let me comment that in, or check that in here. So here's our first version of it. And version 7. Okay. All right, and notice I could just test it one line at a time, right? So let's do the application line now. Okay, so here we're going to have an application. Once again, I'm going to want to have a fresh to introduce some logic variables. I'll say E1 and E2. And the syntax of an application is that we have term E1 applied to term E2. Okay, so that's what that looks like. Now, go ahead and check that in. All right, so we're 2/3 of the way done, and I could test that also, but I've got some confidence in it. So let's now do the last one, which is the variable x, okay, or some variable, and we're going to represent a variable as a symbol in Scheme, a Scheme symbol, and so we've added to sort of the core logical foundations of miniKanren a few constraints that make it easier for writing things like interpreters and type inferencers and type checkers and grammar-based programs. And one of the constraints we have is called symbolo. So symbolo. So if the term is a symbol, then we say, hey, that's a variable. That's syntactically legal. Okay. So symbolo is the last way we can represent. And we're not actually saying we don't care if it's X or Y or whatever, right? But we care that it's a symbol. So let's see if that runs. Yes. Okay. Cool. And we can try, if we want, some other tests. So we could say, well, actually maybe it's lambda, z and z applied to z or something like that. Okay. So we got an application, we have a variable reference, and we have a lambda. So let's see if that's syntactically valid. Yes, that's syntactically valid, okay? All right, so we've implemented our grammar, and we've got all that stuff working, and let me check that in. And this is check-in number 9. All right, cool. Now, okay, that's kind of cool that we can write that. But what would be more cool is if we can use those logic variables we've been using other places, if we could actually use that inside of our call to lcsyn. So right now, we're having to give a fully ground or fully specified lambda calculus term. And we're checking, we're verifying, validating that term, make sure it's syntactically legal. But it'd be really cool if we could instead put in a logic variable and say generate a valid lambda term. So let's try that. So I'm going to get rid of that term. And I'm going to put in my term, or I don't know, I'll just call it Q for query variable, okay? So now I've got this query variable in place of the call. And let's try doing a run now. And so the first answer is yes. So we're getting back this _0 thing bound to Q. That's, if you remember, that's a representation of our fresh logic variable. And we have this side condition. The side condition is saying that that _0 thing has to be a symbol. So it has to be if you were ever to instantiate it to a ground value, it would have to be a legal scheme symbol. And scheme symbols are how we're representing variables. So what this is saying is that any symbol, that's fine. That's just a lambda calculus variable. Okay? So that's actually representing infinitely many concrete values, infinitely many ground symbols. Now let's see if we can get another answer. Okay, here we're saying, if we have a lambda term and it has the right structure, has parentheses and something, that's fine. And if it has something else in the back and could be different, that's fine. That's not very constrained. But, okay, that's fine as far as it goes. What about this _0 thing? What should that be syntactically for this to be legal? Symbol. Should be a symbol. Okay, so maybe we were a little sloppy. Let's go back. And so we can add a side condition maybe. Okay, so what else can I write here to kind of lock it down a little more?
Symbol X, symbol
So I can do symbolo X, okay, and symbolo T. So do we know if T is actually a symbol? That's a good question. What is T? It's an arbitrary lambda calculus expression. So what do we need to write here? LC sin, yeah, we need recursion. LC sin on T. So that was part of the problem. We weren't recurring properly. Anything else you see that's wrong in those along the similar vein? Anywhere else where we were sloppy? Application, right? What about these E1 and E2 things? We're not putting any structure on those. Those actually have to be lambda calculus terms themselves. So we need to recur. LK sim on E1, LK LC sim on E2. All right. So hopefully that will work. Let's see. Sin. Okay, sin. Good. Thank you. Ah, okay, cool. So let me paste that in. All right, so this is check-in number 10. All right, so if I run that, let's see. So we have the symbol answer like we had before. Ah, okay, so this looks better. So now when I get a second answer that I'm generating, it's like, okay, well, it still has that same structure we saw before, but now we have some side conditions. We're saying _0 has to be a symbol. And here we're saying the body is a symbol in that case. So this, and they could potentially be separate symbols, but they could be the same symbol. That's what having the _0 and _1 means. So this could be lambda ZZ, or it could be lambda ZW or something like that. Those would both be legal. And I can ask for more. So here's an application where you have a symbol applied to a symbol. Okay, and I can keep generating more of these. So here's a lambda whose body is another lambda, right? So now I can generate these and I can enumerate every possible lambda calculus term syntactically, right? Okay. So that's basically the cool idea about pure logic programming. And miniKanren is really a language for pure logic programming, where the idea is you can just write down a mathematical specification, something like that, and have something close to the math. And then once you have that, you can just use the same code not just to check that something's correct, but also to generate answers. All right, so let's do this. Okay, so if, what I'm going to do is I'm going to refresh Venire. Just refresh the browser. Make sure it's not in a goofy state. And you can see up top there are some different programs. So let's see if I try type inference. Okay. So if I go to type inference, you can see that we've got this miniKanren definition called bang /0 or -0 or something. Okay. What it's supposed to look like is a turnstile operator in logic. It's supposed to look like one of those special symbols that you saw in Phil's presentation. So this is going to be a type inferencer. And if you've ever used a language like ML, for example, you know what type inference is. You can write down an expression, and the type inferencer will try to figure out what the type of that expression is. So here we have three moving parts. We have the expression that we're going to type infer. We have gamma, which is like a type environment. It allows us to accumulate information about the subparts of the expressions, what those types are. And then type is the type of that expression. All right? And you could see actually already what some of the similarities are. So symbolo expr, this is the symbol case. This is our variable case, right? And in this case, instead of just saying, well, that's it, you have a symbol, now we're going to look up in the type environment what that symbol is, what the type of that symbol is, because hopefully this is not a free variable, this is a bound variable. And we might know that that variable, for example, is bound to an int, has type int. Okay? And there's some other cases, like, for example, is the expression coming in a number? So number is another constraint. And if so, we're going to say the type of that subexpression is int. Okay, that's our int type. So 5 would have type int. If it's a Boolean, like #f in Scheme, it's going to have type bool, and so forth. And then we're also going to have some more sophisticated rules for lambda. Okay? And if you look at if you look at the lambda rule closely, and if you look at the math that Phil put up or is in his paper, you'll notice that these rules essentially are the same. Okay, so this is what he was talking about with the Curry-Howard isomorphism, and that basically we have a little theorem prover here in the form of a type inferencer. And similarly, we have the application rule, and we also have a special version of let. And we have things like addition and so forth. Okay, so let's just try doing something with this type inferencer. So here's an expression that it comes with, but let's try something simpler. So let's try calling our type inferencer, and we have to give it an initial type environment. And we're going to say that initial type environment is empty. And now we have to give it some expression. I don't know what that expression is going to be. And then it's going to have some type, and we'll just write Q for the query variable for the type. Okay? So what's an expression that we might want to type check? Well, let's do something simple like 5. I'm putting a quote here, by the way, to make sure that, that whatever expression is here isn't evaluated at the host level, at the scheme level, but it's actually evaluated, looked at, that term is looked at in the type inferencer itself. So what should the type be here? What should the type of Q be? Should be an int. Yeah, so that worked. It's an int, okay? And I can do something like plus, right? So plus 3, 4, what should the type of that be? That should be int. Okay, sure enough, we got an int. What about plus hash f4? What should the type of that be? Computer says no. All right. And we can also look at things like a lambda expression. What about lambda xx? What should the type of that be? Well, it should be equivalent to some sort of function type, right? So yeah, so we're going to have something like a arrow a. And you can see that we have a fresh logic variable, arrow fresh logic variable. So the thing on the left is the input type for the function. The thing on the right is the output type. The underscore 0 means that this is a fresh variable. It means it could be anything. But the input and the output have to be the same because it's the identity function. Okay? So this is a very general answer. All right? And we could try doing an application. We could try doing something like applying that lambda term to the value of plus 3, 4. And now what type should we get back? Should get back an int. Okay? Cool. All right. So that all works. So this is a working type inferencer. And for the most part, we just kind of wrote down the rules, the math. And, you could take the rules Phil showed and essentially type those in. Now where it gets more interesting is, and this is where the Curry-Howard part really becomes way more interesting to me, is that we can say, because we're in the logic programming domain, we can say that the type is going to be int and that we don't know what the input program is, right? So now we're going from type inference to type habitation or inhabitation. We're trying to find a term that inhabits this type. Okay, so what would be a simple term that would have the type int? 0, okay, sure. Well, 0 is a little specific of an answer. We get back a more general answer that includes 0. We're getting back some fresh logic variable with a side condition that has to be a number. Okay, so that's 0, but it's also 42. Okay, so good question. Are we supporting integers, floating points, so forth? Right now, in this one, we're only supporting positive integers. Actually, we could probably do negative integers. I don't know. This one, yeah, I think this one works with negative integers too. But, well, we could try that. See what the type of -5 is. But I think this is only handling integers. But we could add other constraints that would handle other numeric types. Oh, okay, it doesn't like -5, I guess. So I guess number O in this implementation only handles positive or non-negative integers. But you could add more things. And in fact, when I worked on with Eric Holk and Claire Alvis on this language called Harlan, the original version of Harlan is sort of like a schemely language, but for GPU programming. But it had like an ML style type system, and the original type inferencer for that was written in miniKanren, or cKanren, and we had to extend these operators to handle different types of numbers. So you can do that, you just have to add other constraints. Okay, so what else can we do here? Or what other sorts of things should we get back other than just a literal number? Well, let's see what miniKanren says. So here we have a let. So we're saying let some variable, which is a symbol, which has some number value, doesn't matter what it is, because we're ignoring it, and the body of the let is some other number. Okay, well that's true, that has type in. And it's well typed, it type checks, right? And here's another one. So here we're saying let some variable, so symbol, be hash f. We're ignoring that. We're returning the body, which is _1, and that has to be a number. And so we could play these games, and at some point, okay, so now we get an addition of two numbers. And here, now we start getting into applications. So we're getting a lambda term, a lambda expression, and it's being applied to something, so let's make sure the types work. So we're passing in a number, that's our constraint, and here we have some symbol, and we're ignoring what's passed in, and we're returning some other potentially different number. Okay. So you can play these games all day, and yes, you can. You can keep clicking more answers for as long as you want. All right, I'm going to refresh one more time, and I'm going to show you something that's a little more fancy. But by the way, that type inference stuff, or the type inhabitation, that is the thing that many of the modern proof assistants work on. Okay, I'm going to be Dijkstra'd in 2 minutes, but I'm going to go ahead and show you very quickly what you can do with the relational interpreter. So here we have an interpreter for a significant subset of scheme. It's basically, or extended lambda calculus, if you want to look at it that way. And so we have this eval expo thing, and so we can evaluate an expression. And I think we have something called, eval expo. And let me just show you one query to eval expo, and hopefully this will work. So we're going to call eval expo, and eval expo takes, sort of like the type inferencer, it's going to take an expression and an environment and then an output. So we're going to say, we've got some expression we don't know. We're going to start it in the empty environment, and we want to see if we can create some expression, find some expression that in the empty environment evaluates to itself. Well, let's see if we can do that. Whoa, what is that thing? Well, that's kind of weird. Okay, so we got this weird looking thing. And let me just go to Emacs and start up Scheme. And try to type that in. Format it in a way that's a little easier to understand. And try running that. Oh, wow, I got back the same thing. So that's called a quine. That's a program that evaluates to itself. And by the way, if you look at, here's my last comment that I'll make that's historical. If you look at the micro manual for Lisp by John McCarthy, he says, as a difficult mathematical type challenge exercise, right here, find the list E such that the value of E is equal to E. And that's what we just did by typing in the rules for Scheme and letting miniKanren do its trick. So I hope you'll have fun playing with it. And if you have any questions, I'm happy to answer them.